okay? And he's going to present a non-Hermitian approach to the representability issue in density matrix embedding theory. Let's welcome Emmanuel.
Thank you. So can you see my slides full screen? It's fine.
Yes.
Yeah, okay. So hello, everyone. Well, first of all, I really would like to thank Cheryl and Michael for the kind invitation again. And I'm really sorry, and I mean it, for not coming. I'm completely glued in teaching at the moment, so sorry for that. But anyway, I'm very happy that you could welcome me online. So I'd like to tell you a bit about a different topic, which is quantum embedding theory, and more specifically, the so-called DMET approach that was proposed by Ganeshan and Knissia like 10 years ago. And so for the moment, I would say it is more a numerical recipe than a theory, as you will see later on. So you will understand later on what I mean by that. And that's why I would like to elaborate on and see how we could make the theory more solid from a mathematical and a theoretical point of view. Okay, so let me just give you a brief review of DMET. What is DMET? What's the point about this approach? So, well, the starting point is to consider a basis of localized molecular orbitals. And if you would like to consider lattice, just like a Hubbard lattice, for example, these orbitals, these spin orbitals in black and red, would be just the sites, atomic sites. So why choosing that kind of basis is the motivation is to describe a strong local electron correlation. So that's why DMET has been developed. So obviously, so the idea is to try to evaluate 1 and 2 electron reduced density matrices locally. And obviously, you cannot do that just by extracting a fragment. So if you are interested in these 4 PQRS spin orbitals, for example, you cannot solve the Schrödinger equation just for that fragment. And the reason is very simple, is because that fragment is obviously entangled with its environment, okay? So the idea is to try to simplify as much as possible the environment and reduce the size of the system you will try to solve with the Schrödinger equation. So how do you achieve that? So in DMET, the idea is to perform a unitary transformation in the spin orbital space. So you start from this localized picture, and then you get this new picture. Whereas you can see the only thing that survives the transformation is the fragment itself that you want to embed. And then that fragment is surrounded by 2 types of spin orbitals, the green ones that I will call the quantum bath later on, and then the blue ones, which is just the environment of the bath and the fragment. The blue one will throw it in the trash at the end of the day when we perform the embedding calculation. And again, I'll explain you why later. So the question that comes here is how do you construct the quantum bath actually in this approach? So we realized recently that it can be written in a very simple way as a functional of the 1 electron reduced density matrix, so gamma, okay? So what I just call the density matrix from now on is a very important object in this approach. And to be a little bit more specific, what matters is the block, the environment fragment block of the density matrix. And so the bath is actually nothing but the collection of spin orbitals, and there are as many as the number of orbitals in the fragment you want to embed. And so as you can see in the formula here, you just use the density matrix elements of this environment fragment block to design the quantum bath. So it's actually as simple as this. Of course, if you do that, you don't get an orthonormal basis. So usually what people do, they use a singular value decomposition of this environment fragment block to get automatically an orthonormalized quantum bath. You can also use, that's what we did recently, a so-called Haushalter transformation, but at the end, the bath is exactly the same. So this is essentially how from the density matrix of the full system, you can design this quantum bath. Right, so once you have it, what happens in DMET is that you just close the cluster that consists of the fragment and the bath. So you just close it and you solve the Schrödinger equation for that closed cluster, which means that you do throw in the trash the blue spin orbitals, so the environment. So how relevant is that? Well, so it turns out that this approach, what you're doing here, is actually exact if you treat a non-interacting system. So if your full system is non-interacting, or if you treat it at the mean field level of calculation, it's perfectly justified to throw away the environment of the cluster and just keep the quantum bath. So the important thing you should realize is that when you do this, so the bath is playing the role of an electronic reservoir. So inside this cluster, so the bath plus fragment, you have an integer number of electrons. So this is why you can use a pure wave function, a pure state. And the number of electrons that you describe corresponds to the number of spin orbitals that you have inside your fragment, okay? And I repeat, this is perfectly exact if you have like one electron type of Hamiltonian for the full system. Of course, if now you want to treat strongly correlated systems, you need to turn on interactions inside the embedding cluster, and then the whole procedure is becoming approximate. Nevertheless, the interesting thing is that from that cluster, from that closed cluster, you can evaluate locally at very low computational cost density matrices, okay? Because the cluster is so small that you can perform exact diagonalization, essentially, okay? So that's actually where DMET is an interesting approach. So the obvious question is, okay, right, so you get the quantum bath from the density matrix of the full system, but what is that density matrix, okay? So in fact, there is not an automatic construction of the bath. And so usually this has to be done self-consistently, because you need to start with some density matrix for the full system gamma that then you will optimize. So what happens in practice is that well, people just do a mean field calculation. So which means that they use an idempotent density matrix to describe the full system. That's what you can afford at the size, at the scale of the full system, and you can always construct the quantum bath, of course, on that basis. Okay, and that's what is usually done in practice. So the question is now, how do you get the bath? How do you optimize it, and does it make any sense? Okay, and there are different ways of tackling this problem. So, for example, recently, we managed to write DMET as an exact density functional theory. So how can you do that? Well, if you decide that you will map, so to say the densities that you get at the correlated level inside your cluster, and you're going to map this onto the non-interacting density matrix that you get at the size of the full system. So this density matrix now is becoming a Concham-like density matrix. So asking like a perfect mapping of density, which is nothing but saying you want to reproduce the same diagonal elements of the density matrix. So if you ask for this, then this can converge smoothly, there's no problem, and you get an exactification of DMET, which means that all the correlation effects that come from outside the embedding cluster that are usually neglected can now be described as a functional of the density. Okay, so and that from that point of view, the approach is becoming exact. But this is not usually how it's used in practice. So obviously, if you start to correlate inside the cluster, you are able to generate a correlated density matrix from the embedding cluster. So you get much more information than just the density. And of course, people want to benefit from this. So what is usually done is that in order to construct the quantum bath self-consistently, you ask for the idempotent density matrix of the full system, so the one that generates the bath, to reproduce the density matrix of the fragment that you obtain from your cluster at the correlated level. And that's what is done in practice to the most possible extent. The problem is, like, from a theoretical point of view, this mapping is problematic because it will never work exactly. Why? Because a correlated density matrix is not idempotent, unlike the Concham-like density matrix that is used, that is computed for the full system. Okay, so, and this is exactly the reason why I was telling you that then at this point DMET is becoming a numerical recipe, because you're trying to match things that cannot be equal anyway. Okay, And then the question comes, so does it make any sense? Can we try to improve on this? And can we try to have a more rigorous formulation of DMET, which would, by the way, also enable us to improve the method and design a correlated quantum bath, which obviously would be very interesting. So that's exactly the problem I'd like to address today. And my idea was to try to involve non-Hermitian quantum mechanics for that purpose. And that's what I'm trying to explain you now. So to be a bit more specific, I find this very appealing to use an idempotent density matrix, as is usually done in DMET, because this idea of having a closed cluster is actually coming from this property. So I remind you that this is basically the reason why a non-interacting or mean field embedding is exact in this approach. So if you want to keep like an idempotent density matrix, but still you'd like to store more information about the correlation, so you have to sacrifice something. And then what I was wondering is, can we actually sacrifice the hermeticity? And that's what we somehow are trying to explore recently. So what do I mean by this exactly? Okay, so the whole idea is like, if you have a non-Hermitian density matrix, like the one that I draw here, well, obviously this cannot be your true physical density matrix. So, but my point is to say, how could we use that object to store in one way or another information about correlation? So first of all, if you want to generate this kind of idempotent but non-Hermitian density matrix, well, you need to introduce into your non-interacting or mean field Hamiltonian a term that will break the hermeticity, okay? So I just call this term sigma here. You will understand later on why. And then on that basis, I can generate a non-Hermitian density matrix. The question is, how can I relate this to the true system, okay? So I've been trying to think about some kind of ansatz, or how could we benefit from that? Well, the first observation is, you could always say that, well, the first thing I could do is just try to symmetrize that non-Hermitian density matrix. So if you do this, obviously, you lose lots of information. The only thing that will be preserved is of course, the density, so the diagonal elements of the density matrix. So this symmetric or Hermitian density matrix, I will call it the reference density matrix. So it has some information, especially the density. So I could always try to cook it such that, like the Kohn-Sham system, it reproduces the exact density. But as I told you, I want more. I'd like to reproduce more information about the correlated density matrix, okay? And the question is how to do this. So my point is to say that, well, if at the beginning you have this non-symmetric density matrix, it means that you need to exploit the difference between the upper and the lower triangle of your density matrix. And my point was before, and say, okay, if we start from this reference Hermitian density matrix, and then we try to correct the elements by exploiting this difference between the upper and lower triangle, okay? So it's just an ansatz. I'll talk about how we can rationalize this later on, but that was the original idea, if you want, of the approach. So if I do this, then I will get a new density matrix, which is this one, where I still have the correct density, and now I have these blocks in blue, and of course, by construction, it is symmetrized. So the point is to say, this kind of density matrix, which I don't really know what it is, you know, I need to define it in one way or another, but that density matrix could, in principle, hopefully try to incorporate more information about the correlation. So that was an idea, and I wanted to know if this could make any sense. So I just started discussing with a postdoc who's in my lab, so Sadia Luz, who's developing actually a program where you can use non-Hermitian Hamiltonians. So he's working on open quantum systems. And then he tested that idea just to see if this could work. So the idea was to say, okay, I can calculate a full CI density matrix for some simple systems. So you see, it's just Hubbard systems. And then I'll try to use these ansatz I just talked about and try to see if we can match the density matrices. Okay, can that work? Okay, so we started with the Hubbard dimer, the symmetric Hubbard dimer, and which is just a model for the hydrogen molecule. And so what happened in this case? Well, first of all, he could optimize this non-Hermitian Hamiltonian, so non-interacting and non-Hermitian. The energies always remain real, so there were no imaginary part in the energy. But what's really interesting is that you can, and that you can show analytically, that you can map exactly the density matrix in that case. So this ansatz somehow makes sense. It works. Okay, you can really encode the density matrix perfectly. Then he broke the symmetry of the system, and that observation remained. Okay, so it still works. Then we moved on to more sites, so 4 sites now, and then something interesting happened, that it was not possible with the ansatz we proposed to map exactly the density matrix. However, we still have real energies, and so if you actually compute the kinetic energy, so the orange one is what you get with the ansatz I just presented with the non-hermiticity, and the green one is what you get with the regular Kohn-Sham density matrix. And you see really the substantial improvement, okay? So it clearly means that this ansatz is not completely stupid, because it can capture electron correlation, okay? So, and I found that quite promising. And well, and if you now break the symmetry of the system, you still can make the same observation, okay? So at this point, I would say the question that I asked at the beginning, like, can we exploit non-hermiticity to describe electron correlation at the non-interacting level? The answer is like, yeah, well, why not? But when we got these results, then I started wondering, but does it make any sense? And can I actually try to rationalize this? Okay. So, and that's what I'd like to talk about now for the end of the presentation. So, and the answer is yes. And so how could we do that? So it's quite interesting that I unburied the work I did like 5 years ago that I never managed to develop. And suddenly now with the quantum embedding, this problem is back. So I'm going to try to explain you what it is. So the key argument that I could find here is what actually David Mazziotti used a lot in the 2-electron reduced density matrix functional theory, but it's not really used much in the 1-electron reduced density matrix functional theory. And that is called the anti-Hermitian contracted Schrödinger equation. So what is that? Well, you start from the Schrödinger equation, basically. And well, what you do is you calculate the commutator of your Hamiltonian with a single excitation type of operator. So the idea is you're trying to find a fundamental equation, exact equation, that is fulfilled by your 1-electron reduced density matrix. So for those who are familiar with green function theory, this is very similar to the equation of motion for the 1-electron green function. So, of course, because now you do that, you evaluate the density matrix for the exact ground state, so to say, the anti-Hermitian part of this contracted Schrödinger equation is equal to 0. And this is why it's interesting. Now, if you cook it a little bit, you can take this simple form, which is kind of interesting, where you recover a commutator of the 1 RDM and the 1-electron Hamiltonian, as you would expect for a non-interacting system. But then regarding the 2-electron interactions, they are packed into this operator, a 1-electron operator that I call sigma on purpose. You will see why in a minute. And well, as you can see, so this sigma here, so I give you just the definition. I call it static self-energy because it has a structure which is very, very similar to the self-energy that you see in green function theory. So it consists of the 2-electron interactions. It involves the 2-electron reduced density matrix. So that's why it's an effective operator, and the inverse of the 1-electron reduced density matrix. So the exact equation here, this anti-Hermitian contracted Schrödinger equation that I show again, you see, involves this self-energy. And as you can see, I distinguish the self-energy from its adjoint. So there's no reason to believe that it is actually a Hermitian operator. Okay, this is why you don't have a commutator here. So clearly, if you look at its structure, okay, and then you can show that in more detail, it is clearly not. If you introduce correlation, it is not a Hermitian operator. Okay. So just would like to say that if you know that self-energy, that static self-energy, you can calculate the exact energy also from it, okay, which is an interesting property. Now, how does this connect to my discussion about non-hermiticity? So I have this exact anti-Hermitian contracted Schrödinger equation, and I'd like to see how I can relate what I proposed before this ansatz. Okay, so one thing you could do is say, okay, let's try to solve this equation approximately just by using that self-energy and not its adjoint. So, which means that you would like to set this equation into something like a commutator, okay? So if you do this, well, what that means is you're trying to diagonalize this one electron Hamiltonian, H plus sigma, okay? That is not Hermitian by construction. So then you will get a non-Hermitian density matrix, which is exactly the ingredient I have introduced before. And interestingly, so if you symmetrize it, you will get the reference density matrix that was in orange, okay, that I have introduced. But now the good thing is, like, I can prove rigorously that that reference density matrix is not the exact solution to the problem. So, okay. And how do I know that? Well, I just need to insert it into the anti-Hermitian contracted Schrödinger equation. And if I make the derivation, I realize that basically, because of the non-hermiticity of this static self-energy, it can never be equal to 0. Okay, so so the conclusion is, now I know exactly that indeed, if I perform a symmetrization of this like a reference density matrix, I need to complement it, okay, make a proper correction. So the ansatz we propose is one way to do it. And as you could see, it's not perfect, okay? So we need to work on that. But the whole message here is that this is a kind of interesting and promising idea. Okay, so just to conclude, so as you could see, DMET by construction is ill-defined. I mean, the self-consistency loop is ill-defined because you're trying to map things that cannot be mapped, and deviation from idempotency is a big problem. So one possibility to solve this problem or overcome it would be, so that was my suggestion, to use a non-Hermitian, non-interacting but non-Hermitian like a Hamiltonian, okay? And you can rationalize this by introducing a static version of the self-energy, which is a kind of new flavor of formulation of density matrix functional theory. So what I would like to do now is actually try to have a complete reformulation of DMET based on that self-energy, okay? And my hope is that also connections with the so-called dynamical mean field theory, that is actually the foundation somehow, or mathematical foundation of DMET, okay? Because it was really inspired by this theory that is very popular in condensed matter physics. So I hope that with this formalism, connections between the two theory will become even clearer, and that could clearly be helpful in improvement and development of DMET. Okay, I want to thank my founders, and thank you for your kind attention.
Thank you, Emmanuel, for the great talk. We are open for questions.